I just said you want to try. Alright, so let's make a start. Today we're looking at second derivatives, and second derivatives come up, I guess, twice in the course. In this first SAT, they come up with basically the question of can you find the second derivative, and show simple things about them. In the second SAT, we're more interested in the geometric interpretation of the second derivative and how it looks on a graph. But right now, it's just about finding the second derivative. Second derivative is denoted in two ways: f double dash x, or d squared y on dx squared, read something like that. It is basically exactly as it sounds. Given f of x, find f double dash x. First thing you do is find the first derivative, and then from there you find the second derivative. Basically you differentiate it twice. And yes, there is a third and a fourth derivative if you want to keep going down, but in this case here, I'll just be writing f dash x is 12x squared plus 6x plus 5, and therefore the second derivative is 24x plus 6. So you differentiate it twice to find the second derivative. Now, geometric interpretation is not in SAT 1, but it's worth looking at anyway. If I draw a sign diagram of the second derivative, so you put this in, a sign diagram of the second derivative, where the sign diagram is positive, that means the graph is concave up. It's positively smiling. In the areas where the second derivative is negative, you can probably guess what happens. It's sad. So, what this is saying here is, and this isn't strictly in the SAT, if I wanted to find when the second derivative is 0, I would say 0 is 24x plus 6. X is equal to minus a quarter. What that would imply is the graph is going from happy to sad about this point. So imagine the original graph was a cubic. You guys know how cubics do this. Yeah? So cubicy. It means this point here is the minus a quarter. It's going from happy to sad at minus a quarter. So concave up to concave down is the fancy name for it. The other way we can consider the geometric interpretation of the second derivative is consider it as the derivative of the first derivative. So you guys know when the first derivative is equal to 0, it means you're at a maximum or minimum of the original function, or a stationary inflection. When the second derivative is equal to 0, it means the first derivative is at a maximum, minimum, or a stationary inflection. We'll look at that much more later. Today's more about just finding the second derivative and doing stuff with it. So, let's find the second derivative of this one. F dash x. Alright, so first derivative here is, it's in the form of e to the f of x. So the first derivative will be f dash x, which is 4x multiplied by e to the 2x squared. Alright. Are we sort of happy that's the first derivative by the chain rule? Cool. Second derivative, what are we going to do? Product rule. Nice, because now it's a product of things. Second derivative, we're going to product rule. So then, for f double dash x, we're looking at, well, u is 4x, v is e to the 2x squared, u dash is 4, v dash, and note, often with the e values, you just recycle the work you've already done. We've done this already, so we're just basically recycling it. And there will be plenty of functions that are fairly cyclical. As you go through the derivatives, patterns appear. So from here, we're looking at u dash v plus v dash u. U dash v, 4e to the 2x squared, plus v dash u. 4, not 4. Not 8 either, I think 16.
Oh my god.
I just wrote 4. So 4x times 4x is 16x squared, and then there's this e to the 2x squared. And if you were to solve for this, you would note there's a common factor you can pull out, there's a 4 you can pull out. There's quite a lot of things, because it's cyclical, can then be pulled out. Alright. Yeah. And the same with the next one. Alright, next page. Or the other way around. I'm speaking out loud. I'm thinking out loud. Speaking out loud. My brain's still brain. I'm really sorry. That's alright. Alright. This is not it. Alright. So here we're changing notation and going to dy's. But what it's asking us to show is that the second derivative plus 4 lots of the original function is equal to 0. So our plan is to find the second derivative, then write out this equation with the second derivative plus 4 lots of this, and show that it's going to come out to 0. So we'll see how that goes. First good step is to find dy dx. So we need the first derivative. Does anyone remember what sign differentiates to?
Is it
Cos, positive cos.
no cos? My bad, no positive cos, then negative sign.
Good. So confusingly enough, sign doesn't change sign. So it just goes to positive cos. And are you happy that by the chain rule it throws out a 2? So dy dx is 2 cos 2x plus 3.
Yeah.
Alright. Then second derivative. d squared y on dx squared.
Why is it written like that? D squared y over
Yeah, why is the d squared at the top and then the x squared at the bottom?
It's going to sound bad, but I don't know. And it doesn't matter. It's just the second derivative. I'm sure Google will throw out a good answer, but I don't have a good answer.
In the test, if we accidentally make the y squared,
I don't care. Yeah, I won't mind if you flick the squared on the other one.
I mean, are we allowed to just use f dash x, f dash dash x? Or do we have to do it like that?
If they sent it like this, might as well keep it like this.
D squared y on dx squared, just go to dy on x squared.
That's good. It doesn't work out like that. These are functions and they can't be cancelled out. Yeah, otherwise that would have been nice, yeah.
actually,
Alright, so let's differentiate this. As Lee said, cos will differentiate to minus sign. So in this case here, we're going to throw a negative, and that's going to become sine 2x plus 3. Are you happy that this will throw another 2 out? It'll throw another 2, combining with that current 2 to put a 4 there.
yes.
Alright, so now, let's look at the second derivative plus 4 lots of the original function. The second derivative is minus 4 sine 2x plus 3. If we add on 4 lots of the original function was sine 2x plus 3. Are we sort of convinced that's 0?
Yeah.
Yeah, minus 4 lots of it plus 4 lots of it, yeah, equals 0, as required. So often, they will then ask you to show something or combine something, but that's part of the fun of it. So second derivatives is really just excellent practice of all the derivative stuff we've done so far. And that's why it's such a nice little end of the topic. So, second derivatives. You won't have time to finish them today, so I'll give you some of Wednesday's double as well, but make a start on what you can there. Please.